Thank you very much. So I would like to, of course, thank the organizers for the kind invitation. It's a great pleasure to be here. I think it's my second time in Vienna. Always nice to come back. So since one of the organizers was Matteo, I thought it was just fair to talk about some joint work. So most of it is it's more, if you want, a review on a series of work we did together, also with Berardo Ruffini. So usually when I write a GNR, this is for with joint work with Matteo and Berardo. So we were interested. Start with the model and well-posedeness. We started working on this problem, I think, around 10 years ago, and so we were interested in a physical model for charge equidrops. Maybe the physical model also debatable. But okay. So you have this drop E, and you put some charge, which in the physical case will go on the boundary, and the amount of charge is what I would call Q in general. And you would like to describe the equilibrium shape of these drops. And so it was predicted by Lord Rayleigh, actually in the 19th century, that if the charge is small enough, then the droplet should remain circular, so round. And then if the charge increases, then it should start to squish a bit. And if you increase it even more, they will start to develop some singularities, which are known as Taylor cones. And so it's kind of a very intriguing phenomenon. So far, I think more or less nothing is known on these Taylor cones. And I'm mostly interested in the regime where you expect to see a round shape, and the aim is to justify this as much as possible. And so if you look at his paper, basically you can infer the following model. So okay, I will write directly a kind of a generalized version. So for me, alpha is a parameter between 0 and D, where here the drop is in RD. And what I call E alpha of E, so it's the energy which comes from the interaction between the charges. So it's the minimum between all the possible distribution of charges. So all measure mu, which are probability measure on E. So mu of E is equal to 1 of the double integral of d mu of x, d mu of y, divided by x minus y to the d minus alpha. If I have two charges which are sitting at x and y, the way they interact is through this kernel here, 1 over x minus y to the d minus alpha. And the maybe physical case, Coulomb, would be d equals to 3 and alpha equals to 2. Okay, so you have 1 over x minus y to the power 1 as an interaction. But of course, it's a very quick generalization to look at this type of problems. So the model we look at, or would like to look at, is the following. So we want to minimize among all sets which are volume, let's say the same as the unit ball. We have two terms. We have the perimeter of E plus Q squared times E alpha of E. And here, let me make a first observation, is that for me, so P of E will be the d minus 1 Hausdorff length of the boundary. And I will not too much go into specifics of what kind of sets I'm looking at. So, if you work with usual isoperimetric problems, the natural class in which you expect compactness, it's this class of sets of finite perimeter. It's a bit redundant definition, or de Giorgi sets. But here, as we will see, if you work in this class, there is some issue in what you mean by this term here. So in the end, you always want to work with somewhat smooth objects. And one of the subtleties is to understand how what's the right class to work in and how you get existence, and etc. But I will skip completely this part of the question. Okay? So don't be too worried about that. And so what kind of surprised us first and got us more interested to look at this problem was the following, I would say, theorem, but it's quite a simple observation, actually. Is that if I take maybe another thing. when alpha is equal to D, by this I will actually look, so this should be to the power 0 here, and actually I will look at the logarithmic kernel. So minus log of x minus y as kernel. So you could say that Coulomb is alpha equals to 2 in arbitrary dimension, and so if you take alpha equals to 2 in dimension 2, you naturally end up with the logarithmic kernel, so it's also quite natural to look at this case. And we'll see this coming back later on. So what we observed is that if alpha is strictly less than 1, then the problem is ill-posed in the sense that the infimum of the energy the same as the perimeter of B1, which is strictly less than the energy for every reasonable set E. And so basically, if you try to minimize this problem here, you will just have this term here disappear, and so it's boring. So why is that? So it's a simple computation, but I will do the details since it's kind of explain what's happening. Central for the whole talk. So you just construct a competitor which in the limit will give you energy equals to the perimeter of B1. So what you do, what you would expect, so you take one big ball, so this is radius 1 minus epsilon. And then you add a lot of very tiny droplets. And this one, they have radius r. You have n of them. And you can think of them as being infinitely far apart. I mean, I draw them faint distance, but so if they are infinitely far apart, they are not going to interact with each other, and they are not going to interact with this one. So, of course, you can first compute the perimeter. Let's call this E. Epsilon. So this is the perimeter of the big ball plus something else, and this something else is a big O, so there are some constants I don't care, times the number of balls, so n times their perimeter, so r to the d minus 1. Okay, sorry, maybe here I should add that since you have a volume constraint, you have that n times r to the d would be like anyway, just things to make the volume right. And then if you compute E alpha of E epsilon, so okay, here it's enough just to have an upper bound. So what I can do is put 0 charge here and do a charge 1 over n on each of them. And since the energy is quadratic, I get n times 1 over n squared. So this is less than some constants, 1 over n, times the energy of one ball. And this, by scaling, you see that this is like 1 over r to the d minus alpha. So now what you want is to choose n and r in such a way that both of these terms are small. Okay? So this one will disappear, and this one will just tend to P of B1. Okay, so you make the ansatz that draw the note so that r is n to the minus beta. Okay, so I'm thinking of n going to infinity, so r should go to 0, so that should be the action. And I want to choose beta in a proper way. So now you see that if I look at the first term here, so n rd minus 1, this is n to the 1 minus beta d minus 1. So if I want this to go to 0, I want the exponent to be negative. So that means I want beta to be larger than 1 over d minus 1. And then I want 1 over n, 1 over r d minus alpha. So this is n the beta d minus alpha minus 1. So I want beta to be less than 1 over d minus alpha. So you want to be able to make this choice, you need that 1 over d minus alpha is larger than this, and this is exactly the condition that alpha is less than 1. Oh, sorry, larger than 1. Blah, blah, blah. Sorry. Right? There's also a little bit of confusion in the literature, in particular in our literature. So what we wrote is that sometimes we switch from the power d minus alpha to the power alpha, and then it's a bit of okay, so if you want, this is a proof, but in hindsight, this is not so surprising. The following reason, not so surprising. Because oftentimes people look at what's called the alpha capacity, so cap alpha of E. This is 1 over E alpha of E. And what is known, if you look, for instance, at the book of Mattila, is that this is a bit like H d minus alpha. It sees sets of dimension larger or equal to d minus alpha. Whereas the perimeter of E, I said this is H d minus 1 of boundary of E. So this sees set of dimension larger than d minus 1. You see that if alpha is strictly larger than 1, I can modify my set E on sets which are big enough for this one, but small enough for this one, if I make it correct. And so I can make disappear the term E alpha without touching the perimeter term. And then there is another observation which is kind of going in the same direction, but which came quite a bit after this first paper, is the following lemma, which actually not very hard to prove. We have set F, which is inside E, and such that the difference is inside the ball of radius R. Then I can estimate the difference of the E alpha energy. So E alpha of F minus E alpha of E. This you can estimate by R to the D minus alpha. Whereas if you look at the difference of perimeters, this is not always true, but what you can expect is that this will be like R to the D minus 1. And so you see that if alpha is larger than 1, then actually this term will be dominant. Because the power here is decaying slower than the D minus 1. Then the question that is very natural to ask is how can you reconcile this kind of observation with the fact that in experiments and in numerical computations, you do see something. And in particular, you see the ball as a natural object coming when the charge Q is small. So how to reconcile this with experiments and numerical. So kind of the question is, what is the mechanism you should add to your model to recover a well-posed rational problem and to have that, hopefully, the minimizers for small charge are the balls. So the aim of the talk is kind of to describe you a few options that we explored. So the first one is if you just look at the stability question of the ball. If you want, what this result tells you is that if you take a very wild variation, then the ball is unstable. You can see what's happening for less wild perturbation. So what we proved actually in 2 papers is that the ball is stable for small q. Under a small C11 perturbation. and this is for alpha less or equal than 2. And then I will come back to this in a second. And then this was improved in an extremely elegant paper by Raphaël Prunier. So this is only for the Coulombic case, so alpha equals to 2, which one could argue is the most interesting one, where he proved the stability for small Lipschitz perturbation. And actually, this result is optimal, because there is an example which is due to Matteo and Kirill Muratov, which shows that the ball is never stable if you take large enough Lipschitz perturbation. So you cannot go better than the Lipschitz class. And as a consequence of this result, is that balls, they minimize in a class of convex set. And we obtained a similar result before in dimension 2. So since you expect to see first the ball and then something a bit squashed, one natural constraint you can add is convexity, because you say, okay, you expect your solution to be convex, so let's just restrain to this class. So what these results tell you is that indeed in this class you recover the behavior you expect. So as a side remark, in the convex class, it's quite easy to prove that you always have existence of minimizers. Because convexity is a very strong constraint. Usually, how do you prove that balls are minimizers for this type of problem? So there's been a lot of work around looking at perturb isoprometric problems, so things of the form of P plus something. Well, the something is usually something non-local, and maybe the most iconical example is the Gamow liquid drop model. And so usually the proof of the minimality of the ball for epsilon here. The proof of the minimality of the ball for small epsilon usually goes in 2 steps, which are inspired by a proof of Cicalese and Leonardi for the quantitative isoprometric inequality. Is first you prove uniform regularity estimates on minimizers of this problem, so uniform in epsilon. That implies that the minimizers, when epsilon goes to 0, will converge in some strong sense to the ball. And then you do a kind of second-order Taylor expansion, which is what I will call here the Fugglede type argument. And so if you want the results which I described here are these kind of Fugglede type computations. But there is an important difference between, if you want, this result and this result, is that in the case of Prunier, since he was able to prove that you have a stability for small Lipschitz perturbation, because of the convexity constraint, you get for free that when the charge goes to 0, the ball will converge somewhat in the Lipschitz sense to, the minimizer of the problem with the charge will converge to the ball in the Lipschitz sense. And so then you don't have to work for this regularity part. Whereas in this result here, we first prove a higher regularity and then use the kind of this step here, which was working only for C11 function. And we'll see this coming back later on in the talk. Okay, so another possibility, which was put forth by Matteo and Kirill Muratov, is to put in the functional something which is penalizing a very strong concentration of measure. So look at E alpha, let's say K of E, which is the mean among all probability measure of so the same function as before. Then you add penalization of the L2 norm of mu. So of course now the measure has to be in L2. So this model was studied by De Filippis, Hirsch, and Vescovo. And there's also a combination with another paper by Mukozeva and Vescovo, where they prove that if I fix the K here, then indeed the balls are minimizers for Q small. And they really followed the program I was describing. Means that in this paper, they prove uniform regularity estimates on minimizer of the corresponding problem. And then in this paper here, they did the Fuglet decomputation, which is quite involved. And actually here, I'm a bit unfaithful to their result because they looked at a slightly more complicated problem, but then the proof becomes also more complicated. Then in the list, one natural thing to look at is also what's happening when you don't have the observation there. So what's happening when alpha is less or equal to 1? So so the result is what you expect. So again, it's with Matteo and Berardo, is that balls minimize for small charge. And as you can imagine, alpha strictly less than 1, it's the easy case. Because if you admit that you have minimizers, then because of my observation somewhere, this one, then you see that your minimizer will be actually a standard quasi or almost minimizer, depending on your favorite denomination of the perimeter. And so the classical regularity theory for almost minimizer of the perimeter applies, and so you get regularity. And so the real question is what's happening for alpha equals to 1. So this is the critical case. And so thanks to this lemma, what you get is that minimizer, if they exist. So sorry, before I talk about this, there was a first case which was treated by Matteo, Berardo, and Kirill Muratov. So they looked at the case D equals to 2. So this, one can argue that it's also a physically meaningful case, because this is the case where you have a drop which is kind of trapped in between two plates, so it has to live in a two-dimensional setting, but it interacts through the real Coulomb kernel. Okay. So the interaction is through the 3D Coulomb kernel, but the drops are confined to be 2D. And so in this case, they prove something very sharp, is that there exists a charge Q0 such that if Q is less than Q0, then minimizers are ball. And if Q is larger than Q0, then there is no minimizer. This is kind of the dream statement that one would like to also have in the Gamow case, but there are only very few examples when one can prove really the full picture. But they used very specific 2D arguments. So. Then the question is what's happening in higher dimension, in particular if you are in 3 dimension. So, what you see is that if you have minimizers, then they will satisfy the following almost minimality property, is that P of E is less than P of F plus Q squared times R to D minus 1. This is for every F inside E with symmetric difference in BR. Maybe a small comment. I'm always putting this condition that F is inside E, because if you do outward perturbations, then the E alpha part of the energy is decreasing, and so you just get the same inequality without the extra term. So this is kind of the more interesting case. So you see that here, this is exactly critical for the regularity theory for minimal surfaces. But what you can play with, so it's not you cannot gain from the power here, but what you can use is the fact that you are interested in what's happening when Q is small. So when Q is small, this is still a small perturbation of perimeter, not as R goes to 0, but anyway. So what you can prove is that you can run the kind of classical excess improvement scheme, And what you can prove is that if the excess is small, and I will not get into more details, then, so let's say in scale 1, then the excess remains small for every smaller scales. So the excess is not going to go to 0, a priori, but if you have a smallness excess information at one scale, then it will propagate to smaller scales. So in the end, the conclusion of that is not that you are C1 alpha, but you are kind of flat at every scale, which, if you want technical terms, that means that you are Reifenberg flat. So using this, prove what's called Reifenberg flatness. And if you want, formally, this is a bit like a Hölder type continuity property. That means you are kind of Hölder for every exponent. And once you know this, you can improve what you know on the solutions. And I think this is kind of one of the nice insights. Is that, okay, now I will introduce another player in the game that we didn't see yet. So if I look at the potential, so u of x is the integral of d mu of y divided by x minus y to the d minus alpha. So okay, d minus 1, since here alpha is 1. So that E1 is just the integral of u against d mu. And what you can see, so this is exactly the kind of things that we saw in the previous talk when we saw this fractional derivative. This is the Riesz kernel. And so what you can see is that this function here solves the following PD. So minus Laplacian 1/2 of u is equal to some constant, which is a dimensional constant, times mu, where mu is the equilibrium measure. And in particular, it solves minus Laplacian 1/2 of u equals to 0 in the complement of E. And so there has been quite a lot of activity around the boundary regularity for solutions of PD in rough domains. So here E is only a Reifenberg flat. So what you can see is that if E is flat enough, then you get the same type of boundary regularity as for a smooth object. And so you get that in the end, the measure here. So maybe another comment is that in the case alpha equals to 1, the optimal distribution of char will live inside the domain, and it's going to explode next to the boundary, and it's going to explode like the distance to the boundary to the power 1/2. So minus. Now you have this extra information here, and you can run a second kind of quasi-minimality argument. So this is inspired by the paper by De Filippis, Hirschevesco. What you can prove is that, as before, if I have a competitor F such that the difference is in BR, then perimeter of E is less than perimeter of F plus, okay, Q square times the integral on BR of mu, the 2D over D plus 1, the power D plus 1 over D. And so what you see is that, so if you started from the beginning from this property here, you're not able to say much about this quantity. You don't even know that it's finite. But now that you know this, you can prove that this is actually estimated by Q squared R to the D minus maybe some small epsilon. And the epsilon here is only depending on how flat is the set. And so now once you are here, you are in safe land, because this is again classical quasi-minimizer of the perimeter, and so the Georgi theory, or Allard, Almgren, everything applies. And so you get C1 alpha regularity, and so you're back in the usual story. And kind of the moral of this story, and maybe even from what was before, is that if E is flat enough, then mu behaves well. And so you get a better quasi-minimality property. This was... I have 10 more minutes? No? Okay, so this was kind of treating the non-Coulombic case. So another very natural idea, which was around for a long time, but it took us a lot of time to make it work, is to add a higher order regularization. So this is, let's say, for concreteness, let's look at, sorry. This works for d equal to 3, but for a slightly more general class of alpha, but let's look at the Coulombic case. And so you might want to consider, so it's going to look like before. Now I add a parameter lambda in front of the perimeter. And then I add Wilmore energy. This is the same object that we saw in the talk by Fabian Rupp. So W of E, so this is the Wilmore energy. It's 1/4 the integral of h squared, where h is the mean curvature. And okay, so the idea is that this should penalize variation of the curvature in a L2 sense. So this should give you a bit more regularity, which then would kill the kind of singularity coming from this term here, and you should be back to a more regular situation. So the theorem is that indeed it works. So balls minimize so the part without the perimeter. So if lambda equals to 0. And of course, since balls are isoperimetric sets, they are also going to be minimizers for every lambda positive. So this is kind of the hardest statement you can make, and then minimizers for this follow directly. And the proof, I mean, the central ingredient of the central step of the proof is to prove, if you want, existence and uniform C1 beta regularity for the boundary of E. Maybe I can say a few things about that. So actually here we are in a much simpler situation than what Fabian was describing, because we don't have the spontaneous curvature. So in particular, when Q is small, we have that you just make a test with the unit ball. So what you see is that the Wilmore deficit, this is estimated by Q squared. So this is a very simple estimate, which is going to 0. So the Wilmore energy of E is going to the Wilmore energy of the ball. And that means in particular you can apply a very strong result by Delelis and Müller. Which tells you that you are actually a small W22 parametrization of the ball. Psi, which is conformal, such that boundary of E is psi of boundary of B1. And you have the estimate that psi minus identity W22 squared is estimated by Q squared. So we are converging in W22 to the ball. But this is, so one could think, okay, I'm back like in the situation of the convex sets, where kind of just because of the energy, I have a good convergence, and now I can do my Fuglet argument. However, this doesn't quite work, because here, so the Fuglet argument, it works very well when you have graph over the ball. And here, it's a small totality, but you have small parametrization of the ball. And since, so here your object, so boundary of E is of dimension 2. You see that W22 does not inject in Lipschitz. So the fact that you have a good control on W22 does not prevent from having normals which can vary a lot. And so this, at least for us, was not enough to conclude. So we needed to improve this regularity, and so still run a regularity argument. And maybe for the sake of time, I will not go too much into that. But basically what we did is that we reproduced the proof of Simon of regularity for minimizers of Wilmore with constraints of the genus. along the line of what also Marco Pozzetta did in the paper that was mentioned by Fabian. Maybe one small comment is that in that proof by Simon, there's a very large part and technical, which I have to say I never really understood, which is about treating what's called bad points, which are points where you could have concentration of the W22 norm. And here, because thanks to this good parametrization property, we are able to avoid completely these bad points and prove that they don't exist. And so the proof becomes much more simple than the one from Simon. So somewhat here, we are mixing the parametric and non-parametric approaches to get the best of both worlds. Should I stop now? Can I talk for 5 more minutes, or is it 5 minutes including questions? I would rather leave time for questions. Okay, maybe I can just talk about what kind of things we are looking at now. So since it felt like we understood fairly well this case, it seemed natural to look at the capillarity version. There's actually some physical motivation for that. This is a kind of ongoing work with a joint student of Matteo and me, Adriano Prade. So now we look at the capillarity case. So now on top, so it's the same problem as before, but now you are sitting on top of some substrate H. And you have an energy which looks very much like what Antonio was describing, and I think you're going to hear a lot about that in the next few talks also. And you want to minimize. So H plus is what's above, and H will be just the line. So same as before. Now I put the mass constraints to be B1 plus. So okay, I just say what is this in 1 second. Of P beta of E plus Q squared E alpha of E. And what I call beta here is what Antonio called omega. And so if I am minimizing this term like that, I will get as B1 plus. So B1 plus will be the truncated ball. So this is B1 plus. And here the contact angle is gamma, where cos gamma is beta. And what I call P beta of E, it's HD minus 1 of boundary of E intersected with H plus minus beta of the wetting region. So of course, just like before, if you work in the Georgi class, you will have ill-posedness when alpha is larger than 1. And also another comment is that if you work in any regularized class, even in the smooth case, you cannot expect B1 plus to be the minimizer of this problem here, because it's not even a solution of the Euler-Lagrange equation. The result cannot be that for small q, you are exactly equal to this. This problem actually was considered quite a lot in the physics literature because it has connection with what's called electrowetting. And even before that, there was some prediction by Lippmann. I don't know how many N's and P, but I think it's like that. It's around the same time as Lord Rayleigh. And his prediction was that as soon as you put a little bit of charge, the contact angle change. And there is even some prediction that's called the Lippmann law. And so there was quite a bit of debate in the physics literature whether or not you keep this Young law, like the usual one, or do you have a new Young law which is following this Lippmann law? So what we could prove, and I will stop there, this is in Prade, is that if you minimize the non-convex set, you have cos gamma equals to beta. So in this case, you do have the, and this is for dimension 2, and alpha equals to 2, so the same setting as what we did with Berardo. And I think I don't have time to talk about how you prove this, but here, and of course, one of the main questions is what's happening in dimension 3, but